All right, welcome everyone to the last and final day lecture. Thank you for coming. A few announcements for today. Project 3, due tonight, 11:59. Your last homework, due tonight, 11:59. After that, no more homeworks and no more projects. Yay! If you are in some crazy time zone where the final exam time just doesn't make sense for you, please fill out our final exam time conflict form by Monday. We have a link on the course webpage. And please fill out the course evaluation forms. There's two of them. There's one that's linked to on the homework. That's for our internal use. We'd love if you'd fill that out. And then there's also one from the campus, really, really important and helps us improve the course. So we'd love if you could fill that out. And if 80% of you fill that out, we'll give you two points back on your final exam. Final exam time is on the course website under the policies page. 3-hour exam. It'll be an online exam. Okay, so what I thought I'd do today is I'd do just kind of walk through what did we learn this semester. What did we learn? Well, goal of this course was to give you a little bit of an overview of data science. I'm hoping this will be relevant to you in your lives. One of the trends we've been seeing over the past few decades is a lot more access to data. And that means we can discover new stuff and can make more informed decisions, can use the evidence to help us guide what we're doing. And so this class was trying to help you, give you some techniques for working with data. One of the themes in this class is that we marry computation and statistics. And so the hope is that you find computation to be a really powerful tool to help you do this kind of data analysis, visualization, prediction, inference. And the hope here, one of the things I find really inspiring about data science is that we're not just arguing, I think this, well, I think that, I think this, well, I think that, is that we can look at evidence. That we can, when we have some data, we can, that gives us some facts, and we can form some evidence that everyone can analyze, and that gives us an objective basis for making a decision, and I think can potentially, ideally, hopefully influence people and change society. Is the final designed to take 3 hours? I don't know. Professor Sahai is writing this one. I think it's probably will take most of the time available, but it'd probably be similar to previous final exams from previous semesters. All right, and last, data and computation are everywhere, and so understanding it is really important, so that other people can't snow you with statistics and claims, and so you can do your own analysis. Some of the limitations of the techniques we've been showing you. We've been showing you a lot of technical methods and trying to show you some case studies where it can be, hopefully illustrate why these techniques we've been showing can be useful. But just caveats to beware. Evidence and quantitative analysis can be really helpful for good decision making, but they're not enough by themselves. And you have to be really careful about what bias can be in the data. Where's the data set come from? What are the, is there an agenda behind it? Who's in it and who's missing from it? Help you have to understand what the right questions to ask are and what the limitations of what you can learn from the data set. So we've been teaching you a lot of quantitative techniques, and I think it's also really important to have this kind of qualitative analysis as well. Okay, so we need both. All right, so themes from how to analyze data. You get a big data set, what do you do? Typically, we'll have some question or questions we care about, something we're curious about from some domain. Start with the data set. Try to identify what assumptions we need to make about that data, how the data was collected, maybe, how the random samples were chosen. figure out some methods for analysis of the data, visualize the data to understand what's going on, explore what's happening, figure out what the right questions to pose are, and then do kind of quantitative analysis to answer those questions. And we've teach you a whole bunch of techniques for that. And then maybe the most important part, don't stop there. Don't stop there with the technical quantitative analysis. You need to then interpret results and explain them in a way that can be understood by your audience. So in the language of the people who care about this, who you're speaking to, trying to avoid a lot of the mathematical and statistical jargon. How not to do it? Sometimes if you take a bad statistics course or a bad computer science course, you may see something that focuses solely on the quantifying. And we spend a lot of time on how to quantify, how to do the technical analysis. But if that's all you do, you can really get in trouble because you're not aware of what assumptions you're making. You can't communicate results to others. So you need to kind of put it inside this this broader framework. And in this course, we tried to give you the perspective of doing both of these using computers as a tool to aid you. All right, so what did you see in Data 8? We showed you table manipulations. We hopefully taught you a little bit of Python. Some of the themes here were working based on simulation. We tried to teach you how to form models of the data and then how to evaluate your models, how to make decisions about whether those models are accurate, and how to use those models to make predictions or inferences about the population at large. We taught you some techniques for estimation. This sampling simulation base is quite unique to Data 8, actually. We tried to teach you something about how to understand the variability in the sample. So when you draw an estimate, how accurate is your estimate? How accurate are your inferences? Tried to teach you how to make predictions using linear regression and machine learning. There's a lot more one could learn. I want to particularly highlight one topic for those of you. I heard from a bunch of you that you really enjoyed hearing about the human and societal impact side of things when we talked about privacy last time. So I wanted to highlight one more. This is not required. It's not going to be on the final. It's not part of the required topics. But if you enjoyed this stuff, I wanted to recommend to you a guest lecture from summer in Data 8 that didn't quite manage to squeeze it in this semester. But there's a YouTube video from Berkeley's own Zayed Obermeyer, who works on machine learning and algorithms in medicine, in healthcare. And he talks in this talk about bias. It's really tempting to think that if we use algorithms, machine learning methods, then because it's a computer working, that they will be immune to the kinds of biases that we as humans often fall prey to. And it turns out that doesn't necessarily happen that way. So highly recommended. I found this lecture so much fun, really, really interesting stuff. What have we learned? What have we learned in class? Well, I kind of wanted to highlight, I think we've come a long way. And so I wanted to give you some examples to maybe illustrate some of the things that I hope you've learned, that I hope you can take away, that I hope will be useful to you in your future life. One thing that I hope you get out of this is that hopefully you now know how to read studies from a more informed and critical perspective. So kind of before Data 8, you might have seen this newspaper headline reporting on results of a study that chocolate, it's good for your heart, right? We mentioned this kind of one in the first few lectures. And then a couple lectures in, we talked about associations. And so if you read that article, you might find in there a quote that said 12% of those who ate a lot of chocolate got cardiovascular disease, and compared to 17.4% of those who didn't eat chocolate, right? So then we talked about was that an association or not, and what conclusions can we draw? And hopefully after the first few lectures, you then were in a place where you could start to talk about, okay, is this an association? What can I conclude? Does this mean that if I eat chocolate, I'm going to be healthier? Is this correlation? Is this causality? So now that we've gotten through the whole semester, I want to actually go pull up for you the paper that was behind this newspaper study and highlight from you that hopefully now you could read these papers. You might not be an expert in public health. You might not know everything that's going on. You might not be an expert in statistics, but it's surprising how much you can understand now about pull up a paper in the scientific literature on some subject like this and get a reasonable sense of what's going on and form your own opinion about what they're finding. So here's a little bit of a zoom in on the results paragraph of this paper. And I've highlighted one sentence in here where the researchers are summarizing their results. This is now not newspaper reporters. This is what was in the published paper. And here it says the multivariate adjusted HR for CHD was 0.88, 95% CI 0.77 to 1.01. Now, I don't know about you. I'm guessing before that class, this class, that's a lot of gobbledygook. But now that you've taken this class, we can actually talk about what that means and maybe you can interpret that. So multivariate adjusted, well, okay, let's ignore that. HR stands for hazard rate. And in project 3, you saw basically hazard rate. So what's hazard rate? It's a ratio. It's a ratio of the percentage of people who got coronary heart disease in the treatment group versus those in the control group. So it's the ratio of those who got heart disease from those who were eating a lot of chocolate versus those who weren't eating much chocolate. Okay, so numbers, smaller numbers indicate that eating more chocolate was associated with less heart disease. All right. So hopefully you can now understand what hazard rate means. CHD, coronary heart disease. Hazard rate was 0.88, so less than 1. Hence the newspaper headlines saying folks who ate more chocolate had less heart disease. And so we can conclude there's an association. And then you can see here 95% CI. What is that? That's 95% confidence interval. And so the confidence interval for that hazard ratio is 0.77 to 1.01. So now hopefully you can interpret that too. What does that mean? What does that tell you? Yeah, 1 is in the confidence interval and 1 has a particular meaning. The hazard ratio of 1 means would mean equal amount of coronary heart disease. All right, so was this, yep. There's a chance that chocolate is worse for you. 1.01 would mean that chocolate was worse. Yep, yep. Yeah, 95%, yeah, yep. 95% of confidence intervals would be good, would have the true statistic in that range. Yep. So was this finding statistically significant? Is this association statistically significant? No, not at the 95% confidence level. So what we can conclude is this could be just chance. This apparent difference, this apparent association we're seeing in the data could be plausibly explained by just chance. Okay, so let's say there is a real difference. Let's say it was real. The hazard rate really was 0.88. Can we conclude that eating chocolate is going to be better for your health? Why not? Yeah, because this is showing an association, but it doesn't prove causation. All right, so then to figure out if there's causation, we'd have to look at the details of the study. And as we discussed in kind of lecture 2, this is an observational study, not a randomized controlled trial. All right, so let's put it all together. Explain without using any jargon, like to a member of your family, what should they take away from this newspaper article? Now that you've read part of the paper. Yeah. Yeah. Okay. Okay. I like that. Yeah. Yeah. Okay. I like your answers. Baloney. There may be an association, but this study wasn't good enough to really show that. Um, maybe you shouldn't trust this headline. Not necessarily true. Okay, great. So good job. So you just did this. You just did this this kind of exercise of diving into the details and then summarizing it without jargon. So what I hope this is getting at is that you can read. You can now. You'd be surprised. You can read papers in the literature and understand a lot of what's going on. So here's another example. Just another random paper pulled up. This was a newspaper headline saying this drug could lower the risk of heart disease. So there's a whole bunch of stuff there. I don't know what triglyceride, lipoprotein, all that stuff is, but we can kind of dive down to that highlighted part. And here they say, patients were enrolled. They say randomized, double-blind, placebo-controlled trial, so randomized controlled experiment. Hazard ratio 0.75, 95% confidence interval 0.68 to 0.83, p less than 0.001. All right, what would that tell you? Statistically significant. Yep. There's an association. Can't plausibly explain by just random chance. Looks like there's something real. There's some real connection here happening in the world. Should I, does this mean that taking this drug is going to lower my risk of heart disease? No. Okay. Is this association, is there any causality here? Yeah. Yeah. It's a controlled, randomized controlled experiment. So we can conclude causality in this case. It's not just an association. Treatment group got the drug. The control group didn't. So it looks like this drug really does reduce the likelihood of well, I don't know, whatever they were measuring, cardiovascular events or something like that, for this population of people. All right. So the relevance of the hazard rate, it's not the key point of this, but just to let you know, it's kind of the rate, it's the ratio of bad stuff happening to those in the treatment group divided by proportion bad stuff happening to those in the control group. Like the likelihood that something bad happens to you if you're in the treatment group divided by the likelihood something bad happens to you if you're in the control group. So a hazard ratio of 1 means it doesn't matter which your group you're in, you have the same risk either way. A hazard ratio of a half means that you have only half the chance of getting the heart disease if you were in the treatment group, if you were taking this drug compared to if you weren't. So that'd be pretty significant. Okay, here's another example paper. These are just some examples. Here you can see this one was about stress. And in this one, the researchers gave the subject some stressful task to do, and they measured levels of cortisol in their, I don't know, saliva. And that cortisol is an indicator of stress. And you can see here that they measured the level of the cortisol after the test compared to before the test, and they're showing here the average numbers, and I think those are probably standard deviations. And then you can see here it says it increased. So sure enough, this really was stressful, or the cortisol really is a decent measure of stress. P less than 0.05, so probably can't be explained by just chance. This is statistically significant. And then you see here this Wilcoxon signed rank test. And oops, we haven't taught you what the Wilcoxon signed rank test is. So that's kind of hinting at that there's still more to learn. There's more to learn about hypothesis tests, but at least you can interpret a fair bit of what's going on in this paper and form your own impressions about what this means. Here's another one. This is a paper on lenders looking at bias in lending, reporting that lenders charge minority borrowers higher interest rates. So here you can go read this social science economics paper and look at their results. And they're also using a lot of the methods that we've taught you here. And here they're reporting that the mortgage interest rate for Latin and African American folks is 0.169% higher than for white folks on average. So that might sound really small. I mean, it's like a fraction of a percent, but if you're buying a house in the Bay Area, I mean, that can add up, right? That could be tens of thousands of dollars difference right there. So that could be fairly meaningful difference. And they're reporting, you know, what they're reporting about this, and they did a model. They constructed a model to try to predict mortgage interest rate from well, they talk about dummy variables. We haven't talked about what that is, and so obviously there's something more to learn here. But they're trying to predict it based on like credit worthiness scores, and then also based on ethnicity, and then they're measuring how much does the ethnicity affect the result. And here you can see here they're reporting. Well, there's some stuff in there that's not quite clear what they're talking about. Fixed effects model, and we haven't taught you any of that. So there's more you could learn, but you can see in there, and they talk about R squared is 0.806. And you know what that is. R is the correlation coefficient. R squared, we talked about what that means. That talks about how much the model explains the variability in the value you're predicting, how much it will reduce your uncertainty in the value you're predicting. So you can see 0.8, that's a pretty high value. This model is pretty good. So, okay. Another example, and here's another example maybe for COVID times. Here's another research paper. You maybe saw headlines about remdesivir, results looking good for remdesivir's treatment of COVID-19 certain patients. Okay, so you could go pull up the paper, the scientific paper that reports on the specific study that was done here, and here we can see what it says here. It says treatment group had a 31% faster recovery time than control group. Okay, so this is a randomized controlled experiment. P less than 0.001. Good. Okay, so that's pretty strong evidence that this is not just random chance. That this drug really is speeding up recovery for this population of people. Statistically significant. Randomized controlled experiment, so we can conclude causality. This drug really is making a difference. And you can also read in here, talks about mortality rate of 8% versus for the treatment group versus 11% for the placebo group, for the control group. So it looks like there's an association there. And then you can see here it says P equals 0.059. So how would you interpret that? Yeah, yeah. We can't reject the null at the 95% confidence level. Right, right. Okay. So this could be due to random chance. Could be. So if you're a newspaper reporter, now summarize this whole stuff. What do people need to know? Anyone have any thoughts? Like you're going to go tell a family member about what this means, or maybe someone in your family has COVID, they're going to be treated with remdesivir. Yeah. Yeah, this will help you recover faster. Yeah, but not necessarily didn't necessarily improve survival rate. Excellent, 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 excellent. Very good, very good. Very good. Okay, so these are real papers, and I hope this was helping you illustrate that. Hopefully you've learned a lot of the terminology and the concepts that can help you understand what you're reading in scientific papers, and also highlights that these techniques, these concepts you're learning here are really widely used across many fields, science, medicine, economics, social sciences, to try to help us understand data and what the evidence is telling us. Another thing I hope you learned is that not just you can read other people's studies, but you can do your own analysis. If you have a question, I wonder if such and such, if you can find data, if you can find a data set, then hopefully we've given you a lot of tools that you can go answer these questions yourself. So hopefully this is empowering for you. All right, so I have a request. At this point, I'm going to kind of take a little break and make a request to you. If you found the course helpful or if you didn't, either way, I hope you'll fill out the course evaluations. These are really helpful to us in helping us evaluate the course and figure out what we can do to improve it. It's also helpful to campus. So hope you'll fill those out. I think that you can go to course-evaluations.berkeley.edu. And if you didn't see it in your email and haven't filled it out yet, please do that. I hope you will. All right. I thought I have some slides here with an overview of all the concepts. So I think maybe what I could do is I could just give you a run through some of these for you fairly quickly. And then you can refer to them at your own leisure. Look a little more if you want. All right, let's see if I can pull up these slides here. Ta-da. Did that work? Didn't work. Sorry for the delay. So the course evaluations, there's two course evaluations. There's one at the end of homework 12. That's our internal one. So please fill that out. But don't stop there. You also need to fill out one from the campus. There's one from the campus. You should have gotten an email. If you don't see the email, go to course-evaluations.berkeley.edu. And you'll need to fill out both of them. They're different. Okay, so some of the concepts we saw here, in this course, saw computation, saw how to describe data, probability, inference, prediction. And I'm just going to kind of zoom past a lot of this. You can refer to this on your own if you want. Here's some of the major topics that we covered in this course. We talked about coding, how to write code in Python, how to do computation, how to work with tables, operations with tables. Some of the big ideas here, how do you organize data? The message in this course was as a table. This is an opinionated course. We taught you our opinions. So you got exposed to our personal views on this. How to work with data. Our view was with operations, you do complicated stuff by combining a bunch of these basic operations that you taught you. So this is what we were teaching you here was basically the next step after Excel. How to work with data and automate some of the computations you might want to do. We also taught you how to compute, and the theme hopefully you got here was to solve complex tasks by combining a bunch of small building blocks. And those building blocks might be either ones we gave you, or it might be that you're building up those building blocks. You're writing little Python functions and combining them and breaking down the problem into small pieces, and that helps you think about things. Yes, these slides are on the website. They're linked to from today's slides. So you can click on the link and that'll take you here. And this is not specific to just Data 8. In Data 8, we taught you a specific package, the data science Python package that was designed to help you learn this stuff in a fairly, hopefully not too intimidating way. It's not really used by the rest of the world. Instead, the rest of the world uses some other technology. But if you go look at the technologies that are used widely, they all share, many of them share these ideas. In fact, they do because we noticed these common themes in widely used commercial software packages, and we kind of stole them and simplified them a little bit. So for instance, most data science computation is done using either R or pandas and Python. Those are the two most common in industry by far. And both of them organize their data with the notion of data frames, which is just another word for tables. If you take a databases class, databases are commonly used to store lots of data. For instance, your bank will have a database that has names of all of their customers and the bank account balance for each of their customers. And databases you can think of as tables And then databases support doing all these table operations. And they do one more really cool thing, which is they allow multiple people to concurrently be operating on the data, modifying the data simultaneously without stepping on each other or trashing anything. So this bank database that has everyone's account balance in it, there's thousands of ATMs around the country, and those ATMs are constantly querying that database and updating it. You know, I withdraw $100 and it deducts $100 from my bank account balance. And if you aren't careful, having two of those things happening at the same time could really trash your data. And databases are really careful to maintain the integrity of your data and support this in an efficient way with really large scale data sets. And if you learn something like Spark, for instance, that basically supports you doing tables and table operations for really big data sets. And the way it does that is by enabling you to do this not on a single computer, but on a cluster of lots of computers. Descriptive statistics. Yeah, Spark was developed and invented by a research group here at Berkeley. Okay, we taught you some ways to describe data set, visualization, and we taught you ways, quantitative measures. They're called descriptive statistics, measures to describe a data set. And some of the big ideas here were use visualization to explore the data. And one of the themes of how we suggest you work with data set is you start with the data, understand what's in the data set, form some hypotheses, some questions, start looking for any patterns or trends that seem like they might be happening. What questions does it raise? This kind of exploratory analysis can help you do that. The statistics can help you summarize the data, and then the visualizations and the statistics can help you communicate your conclusions to others in a really concise and effective way. And so we taught you a lot of stuff, taught you about the median and the mean, taught you about the standard deviation. That's a measure of the variability or how spread out the data is. Most of these are relevant because most of the data you should expect to be close to the average, plus or minus a few standard deviations. So most of the data will be between the average minus a few standard deviations to the average plus a few standard deviations. And if it's the normally distributed, if it's looks like a bell curve, then almost all the data will be in the range average plus or minus 3 standard deviations. So knowing the average and the standard deviation gives you a pretty good idea of where most of the data is located. Taught you about bounds on how much of the data is close to the average. We taught you about standard units. Standard units are a useful way to normalize for the variation. So the z-score tells you how many standard deviations you are away from the mean. Okay, so that kind of gives you a way that's independent of the units you're measuring to see how unusual is this value. Talk about the correlation coefficient, which is a way of measuring the strength of a linear association. Only relevant if the association you have is a linear association. Taught you some probability, taught you how to do calculations, how to do approximations with a normal approximation, how to estimate the size of a sample that you'll need if you want to estimate some population parameter to within a desired accuracy. As a reminder, the probability of some event is the number of outcomes that make that event happen divided by the total number of possible outcomes if all outcomes are equally likely. So we showed you some rules for manipulating probability. We taught you about conditional probabilities, the Bayes rule, tree diagrams, central limit theorem gives you a way to approximate the distribution of the average of a sample. You can review this. You can review this on your own. Inference. No, I don't expect to have a final grade report released before the final exam. We're considering maybe doing one after the final exam as one final one. Sorry, it takes a lot of work to prepare those. Okay, inference, a lot of stuff we taught you. Basic goal is we want to take some information from a sample and extrapolate that to draw a conclusion or an inference about something about the population. Okay, so the theme here is, suppose you did your exploratory data analysis, you found what looks like a pattern in the data. Looks like maybe a trend, maybe an association. Well, it's really easy to fool ourselves into thinking that there's a pattern when there's actually not there. Our brains are incredibly good at seeing patterns that might not be real. So in inference here, we have techniques to figure out, does this reflect something real about the data, something real about the world, or is it just due to chance? And also, we're really taking advantage of random sampling here. Random sampling is our friend because it helps us draw extrapolations about the population from the sample. It ensures that the sample will be representative of the population. And a really key idea here is the law of large numbers, or the law of averages, which says the distribution of the data in a sample will be similar to the distribution of the population. So the histogram, if you were to histogram them, the histograms will have about the same shape. And the larger the sample, the more similar they will be. And if two distributions are similar, that means everything about them is similar. They have similar means, they have similar standard deviations. And so we use this all over the place. We use this with bootstrapping, we use it with hypothesis tests. All right. Yeah, so lots of stuff we showed you about inference, confidence intervals and estimates of a population parameter. We showed you hypothesis testing to help you distinguish between a null and an alternative hypothesis. The p-value is a measure of well, kind of a measure of how much the evidence is incompatible with the null hypothesis. Relates to how confidently we can reject the null hypothesis. Okay. We showed you a lot of different hypothesis testing techniques, how to compare whether two samples come from the same distribution. We taught you how, for instance, if you have a regression line, how to measure whether or not that seems to be equal to 0 or not. Hypothesis tests help you establish whether an association is real or not, whether it can be explained by just random chance or whether it reflects some real association that's actually there in the population. But what it can't do is it can't establish causation. Okay, so it can help you tell whether there really is a difference in the world, but it doesn't tell you why that happens. Unless your data is coming from a randomized controlled trial, in which case you can establish causation. You can establish that the treatment is causing the difference in outcomes. What's the difference between the law of large numbers and the central limit theorem? The law of large numbers says the distribution of a sample is similar to the distribution of a population. The central limit theorem tells you something about the distribution of the mean of a sample. If you draw a sample and you take the mean of that, and you want to know what the distribution of that, the central limit theorem tells you about that. So it's a very specific thing. Yeah, the final exam's cumulative. Okay, we taught you about prediction, how to make predictions using regression models. Lots of stuff for regression. I think I'll just skim right past this. Classification, taught you how to use machine learning to make predictions. So you can take a look at these slides on your own if you like. All right, so what's next? What could you do next? If you enjoyed Data 8 and you want to continue being involved in data science, I got a couple of options for you. One is we have a bunch of data science programs on campus that you might be interested in. We have the Data Science Discovery Program, which is a chance to do research using your data science skills to analyze data sets and try to learn something in support of social sciences or different kind of projects going on. Helps hook you up with some candidate projects where you could apply your skills. Data Scholars might interest you. There's pathways and discovery programs, which Data Scholars especially designed to support folks who come from backgrounds that might be historically underrepresented in data science. So maybe first time in college in your family, or poor, or different supporting diversity. So helps build community and help you be part of a community of others who are interested in data science. We have the data science education program student teams. A lot of the data science education we do on campus is supported by students, by you all, by folks who've taken Data 8, by data science majors who decide to give back to others by serving on these student teams. And there's about a half a dozen different student teams you could explore. You could take a look at the website. All of these links will take you to where you can find more information. Some of these help build content, help build little modules that can be added to upper division courses using data science knowledge in the context of the course. So maybe it's a demography course and there'll be a class or a homework that's applying some of these data science techniques and using it for demography or whatever the topic of that course is. Some of those are helping with the operations of the data science division. Some of those are helping gain leadership, serve other students. We also have a peer advising program where you can advise others who are maybe interested in data science about what the course options are. Another way you could volunteer to help others. You could also join Data 8 next semester as a learning assistant and help out in labs if you'd like to be part of the community. We have this is kind of the part of the pipeline for how we recruit future tutors and teaching assistants is from folks who volunteer to help out others learn the material. So we if you would have any interest in that, we'd love to have you. The Data 8 is successful because of our past students who are so generous in giving to help their fellow students learn this stuff. If you want to learn more, you can click on this link and you can find out application deadlines and where you can apply to these programs and all the different programs that are available you could be involved with. Another option is you could take data science courses. We have a lot of options for more data science courses you could take. Hopefully Data 8 gave you a first introduction, but there's a lot more you could do. We have if you want to go really in depth, we have a minor and we also have a major in data science. If you just want to learn a little more about one or two of the topics you saw here, if you want to learn more about computing, you could take CS88 or 61A. 61A is kind of the first course for computer science majors. CS88 is designed to partner well with Data 8 and teach you what you would learn in 61A that you haven't already learned in Data 8 about computing. If you like more data science, the next course in the data science progression is Data 100. It's a little unusual because we don't tell you, okay, you could take Data 100 next semester. Instead, we tell you, well, go get a little bit more background in computation and in linear algebra before you take Data 100. So Data 100 is kind of our gateway course into upper division data science courses, but you need a little bit more prerequisites backgrounds before you take Data 100. So you'll need to take a course in linear algebra, a math course, and you'll need to take a course in computation. If you enjoyed the probability and statistics, you could take Stat 88, designed to go well with Data 8, or Data 140, it used to be called Prob 140, that has probability, lots more. If you like human context and ethics and the social implications, you might be interested in Data 104, and there are dozens of other courses, and you could go look in to find some examples. You could go look at the data science minor or the data science major. They have a requirement for human context and ethics, and look at the courses that are listed there. There's lots of really cool options there about looking at the social implications of this technology. And we'll post a document on Piazza. Yanai has volunteered very generously to put together one with more courses that might be of interest to folks who've taken Data 8 if you want to go deeper in any of this stuff. Lots and lots of options. Staff, do we have any of the Data 8 staff here? Hi, Angela. I see Yanai is here. So would either of you like to say a word about what your path in data science has been, what your experiences have been, where students could go from here after Data 8, what some of the opportunities might look like?
Yeah, I can start. Hi, everyone. I'm Angela. I'm one of the UGSIs. I also am leading the Data Scholars program. So shout out to some of my students who are here today. Yeah, I'm a fourth year and I took Data 8 in my freshman fall semester, and I've just been on staff ever since. So I started out as a lab assistant and then tutor, and I've been a UGSI for the past 3 semesters. Yeah, so I came into Cal, I guess, undeclared and not sure what I wanted to study, but I took Data 8 as well as some stats, econ, and business classes. And yeah, I think we are all so fortunate to be at Berkeley where there are so many opportunities. And I love how Data 8 and data science in general is just so interdisciplinary. So I hope you all enjoyed learning Data 8, and it's been a pleasure meeting you all.
Let me just put in a little plug about Angela that something you might not know about Angela, and I hope I'm not embarrassing you here, Angela. Not only is Angela amazing, accomplished academic, a really valued member of Data 8, staff member. She is also an amazing athlete, one of the nation's strongest table tennis players. If you're a fan, check her out. And also leading our Data Scholars program, playing a huge role in supporting students and supporting diversity in the program. So proud of you and grateful to have you on the staff, Angela. Yanai, would you like to say anything? No pressure. Up to you.
Yeah, sure. First of all, thanks for Angela for coming today. Yeah, my journey was like the same, I think, as Angela. I took it Data 8 with Professor Wagner and Professor De Niro my first semester as a freshman, and like coming into Berkeley, I had no idea that I was interested in statistics at all. And then like I really liked the course and went on to take a bunch of data science courses, and now I'm minoring in data science. Yeah, so I hope all of you like enjoyed the course as much as I did, and I hope all of you continue to take data science courses at Berkeley with us. And definitely like all the programs that Professor Wagner talked about before, like DCEP or Data Scholars, and definitely like applying to join our staff as well.
Thank you, Yanai. Yanai is amazing. Has just been so active. You can see how active he's been on Piazza. You can't see how active he's been on helping us design course content and create a lot of great material for all of you. So he's been super fantastic member of the Data 8 staff. All right, so we're coming to a close. So I just want to take a moment to thank all of the staff. This course stands and falls entirely on its staff. We have an amazing group of GSIs, tutors, and learning assistants. If you get the chance, if you found them helpful, say a word of thanks to them. They are so fantastic. I really appreciate everything they do. And I'm sure they'd love to hear from you. And with that, that brings our last lecture to an end. And I want to say thank you to all of you for being in this course. It's been such a pleasure to be part of this with you. Really, it's inspiring and really rewarding for me. Thank you all. And good luck on the final. You're going to nail it.